Today I'm doing something different. At any time slot, I can choose 5 hours suitable for myself to participate in Japanese Olympiad Open Contest. But instead of trying to really solve the problems and getting the code done, I will just read them and try to come up with solutions, because that's, to be honest, more interesting for me. I will make some drawings. It might be interesting for you to watch. I expect the video to be around 30 minutes, 50 minutes. If something is very hard, I will not do it. No statement in Japanese, English. Furniture, the first problem. Links will be in the description. And the statement is quite long. In Olympiads, often the samples are very long and description of everything. Okay, we're given a grid with I took some time to read this, and it means we are given a grid. We start from one corner, and in the other we can move bottom and right. And can we get there? Some cells are forbidden. Operations. We try to put furniture. We try to make this cell forbidden. I know a similar problem. Very bad subtasks. So basically, that's a binary problem. I think the solution is to maintain the topmost and bottommost good path. There is a grid. We start in top left, we finish in bottom right. If that's indeed the case, then it's very good that I chose to not do this contest. Some cells are forbidden. And now the two paths, topmost and bottommost, are like that. What happens when a new cell is meant to be blocked? Let's say it's this thing. Then we might update that one of the top or bottom paths. That this one will be updated now to this. But still, it's possible to travel. The issue is, if we later maybe forbid this cell and this cell, the two paths will be like that. And some cells are shared between them. If a cell is in both topmost and bottommost path, it's articulation point. We need to pass through there in order to get from the start to the end. This is start, this is end. The question is just, can I maintain this thing? Whenever I'm hitting something on this path, actually forbidding this for this green path, it also forbids that. And then I'm trying to move like this. But maybe there is something still forbidden here. Like maybe this was already forbidden. Then this kind of automatically forbids this as well. Then we will do this. Do I see details? Just if there is a grid and I maintain, let's focus on topmost path. I maintain the topmost possible path. What do I need to do when one of cells on this path gets forbidden? Then the path becomes like this, and still some cells. Oh, I know. It's okay to always, whenever I change a single cell in this topmost path, actually topmost path is defined by a sequence of n plus n moves, right and down. Like, okay, never mind, that's not important, but it's okay to do things in total in all of changed cells. I mean changed in the topmost path. Because if we start with like top row and rightmost column, at the end we can be only as far as left column and bottom row, but that's in total n times m changes. It's okay if I need to change 5 cells in green path, it's okay to do it in all 5. So whenever something is forbidden, I have new yellow part here. I linearly go through that and check if anything there is forbidden. If yes, if this is forbidden, then I run recursively saying, okay, this is forbidden. Then I have new green path, this. Okay, try to get further and further away from it. Whenever on green path, oh, I see how to say it nicely, I think. Not wrong. I know. If currently this is the green path, and now this gets forbidden, then it means that I cannot go anywhere here. If cell was on the green path and now is forbidden, it means those cells become unavailable as well. So I kind of cut this part out. The drawing is basically description of what is cut out. Remembering green path is equivalent to just remember this area, and this red area we get by queries of type, given this bottom left corner of a red rectangle, mark the rectangle. Okay, so this means that there are new green parts. And now I linearly go through them, I check the new cells, 1, 2, 3, and for each of them, if you are red as well, then cut this out. I think done, and that will be linear. In every, for example, in every row, I will just know how many cells at the end are forbidden. This should be correct, and I'm at 8 minutes or so. Let's move on. As I said, I'm not coding problems. Second problem, monochrome. I solved the first one fast because there was something similar in a Polish competition. And white points and black points in a circle. maximize the number of intersections. Do we have a drawing? A bit boring subtasks, but more interesting now. More drawings? No. I need to, if this is forbidden, I need to read the statement again. Oh, because they connected two black points with each other. I thought that it's about one intersection point. Okay. And up to 8, easy. We just try all possibilities to pair them up. And up to 300. Don't know. Don't know. So in a circle, there are white points. And they said blue or white. I will go with red. 1, 2, 3, 4, 5, 6, and 6. I need to connect them. How will I do it? Can it happen that I connect those two like that and this in the following way? I think it's impossible, because it's only better to make this connection. Right? Yeah. We have one more intersection, that everything that intersected with them earlier intersects with them now as well. The number of intersections didn't increase. It increased by at least 1. Okay, the general statement of mine is, if we have on the circle, if we have 2 white and 2 red, then the blue connections must be like that. And this gives a solution if all red points form an interval. If half of circle is red, the other half is white. Obviously, then this must be connected with something here. What about this point? What do we know about it? Is it true that we choose one connection and it defines everything else? I doubt it. I highly doubt it. Or maybe. I know that if there is any red point here, it cannot be connected with anything white over there. It can be connected with white below or there. The only two possibilities are this and this. If we have this situation, what will change if from this connection I modify it to, let's say in yellow, this connection? Could there be anything here? Actually, I claim that there is no difference, because if there was some connection here, let's say this was red, this was white, but then this is a forbidden quadruple. You see, red, red, white, white, and then it's better to cross them. On the other hand, if this is red, this is white, then this is forbidden quadruple. So there is nothing is connected like that in an optimal solution. The same way, okay, I proved that for blue points, for blue edges. Everything of this form, the number of intersections doesn't change after I flip. And finally, those. But if I have this, it must be of this order: red and white. Otherwise I would flip with this. I'm considering the case of blue edges. If I have them, then this must be of exactly this form. Can there be something pink here? For the same reason, this must be red. And this will be white. Isn't it better now to change everything to this? No. So similarly, I see what it means. There can be a lot of directed edges from white to red, from white to red, from white to red, from white to red, from white to red. Always the start of a segment is white and the end is red. And then it's true that for any two disjoint segments they are in proper order. But still, I bet that this can be improved. Seems to be a hard problem. I will get back to this. Let's move to power, the third problem. I will try this and then get moved to furniture. Not furniture, sorry, monochrome. But for 300 points, I would now check. Actually, even yeah, I would try. If it's easy, if cubic solution is easy, then I implement it. Otherwise, I implement brute force. And with brute force, I check my theorem that it's enough to iterate over a single pair, red-white, and it defines everything, because now if reds are sorted, then second red connect to second white, and so on. I don't know if it's true. Let's try power plant, the third problem. There is a tree. If something is between two vertices, then it's broken. So like it's kind of convex hole of vertices. Drawing, please. Such a long statement and no drawing, come on. Only some vertices have them. I can't believe that there is no subtask with AI equal to 1. Every problem has just n smaller than something. This is not a good IOI style problem set. I recently started more and more caring about that, the number of subtasks, you know. the style of subtasks. Here they are. It's kind of lazy. I'm going to draw the samples and see if I understand them. No. Three, 5, 6, 2. What is on 1, 2, 5, 6 is possible. 1, 2, 5, 6. So this is impossible, this is impossible. And now they are saying turn 1 to 5 on. And then only this is between them. So, and because there is no switch, you will pay nothing. If you turn 1, 5, 6, 1, 5, 6, then in spanning tree, in a tree spanned by those vertices, there is also 2. And you will get 2. If you get 1, 2, 5, 6, this will be broken. I appreciate the explanation. Well, I tried yesterday some CodeChef long challenge problem and it had no explanation. That's stupid. Okay, second tree. Second tree. 1, 2, 3, 5, 6, 4, 4, 5, 5, 2, 7, 2, and 2, 8. Everything has a switch. What can we do? I'm quite sure that it's good to take those 3, even though it will cost us a vertex 2. I think this is optimal. Take 1, 5, 8, 7, then this one breaks, but you get 4 minus 1. That's a 3. So we choose a subtree. In unrooted tree, we choose a subtree, connected subgraph, and we get the number of leaves in that subtree minus the number of vertices of non-leaves, I would say. Let's try the last one. I wouldn't draw it during a contest, but because it's a video for you, it will be nicer if it's drawn. You know what? I will use some online tool for drawing. Be a tree. Did I just add a vertex? No. Annoying. If I click incorrectly, everything is moved. I think we have our drawing. Additionally, some are allowed and some are not. I know what I need to do. Copy this. Paste it here. And remove the forbidden ones. 1, 2, 3, 4, 5, 6, 7, 1, 8, 9, and something. I remember that the last one, 16 was there. What else? 16, 15, 14, 13, 12, 11. Cool. Then I bet that we take... What do we take? 3, 6, 5, 13 and 7. That is stupid. And I can take here a 4. Then it will be 1, 2, 3, 4, 5, 6, minus 1, 5. I think that's the intended, that's the correct answer. What if I didn't take 4? And instead I took 14 and 15? Then I would get 7 green minus 2 bad ones. So again, either I can get it like that or like this, 7 minus 2. Yeah, and I think that's easy bottom-up 3DP, isn't it? Where we have a tree, you can root it in one. And what do I need to know for a subtree? Assuming that I take this vertex and something below, this vertex might be being something inside. Actually, for sure, if I want to do anything in the then this one is inside, or the bottommost leaf. So this is more like white, but there were some edges here, and I took some leaves. Then in this subtree, I just want to maximize, I think, the number of leaves minus non-leaves that are above. It should be very easy to combine multiple children. And just add this number up. If this cannot be negative because it's 0 already if we do nothing. So we take the sum of children. Now there is this guy, and he adds 2 possibilities. If he has a switch, then he allows to be the only leaf, so he maximizes this sum of differences to be 1 if we don't take anything from below, or otherwise it decreases the answer by 1 because we take everything below, but then this guy is bad. It's also possible that this one is a leaf and we take one subtree. So it's maximum child plus 1 for myself, assuming that there is a switch here. I think that's everything. Easy problem, but for IOI, I think. Or maybe, I don't know. Just again, that's a bit binary, isn't it? I immediately came up with solution for 100. Maybe I missed something. I know that there is a leaderboard. I'm quite sure there is one. Ranking site. Yeah. It makes sense. The last problem is very easy. Furniture is also easy. And then a lot of people have 35 here. Let's think a moment more on monochrome. But if I don't solve it in 10 minutes, I will give up. Because I didn't want to spend a lot of time. I will later read the editorial or just hear solution from somebody. So let's try some more with furniture then. No, I keep messing up the names. Monochrome. I'm going to close whatever I don't need. Okay, just 2 drawings for monochrome, the statement, leaderboard. You can close now. This I can close now. The last thing I did is I wondered if this is possible. Actually, this satisfies the thing where we connect red with some white and then everything follows. But I bet that I will improve the answer if I redo this drawing. Let's try red, red, white, red, white, white, red, 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 white, 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 white. I bet that this will be better. So I connect to this white. Okay. A moment ago I had this connection and then everything followed. Yes. So I think that this is better, or even more, this is better. Let's count intersections. 1, 2, 3, 4, 5, and a lot. That many. Those are not straight lines, but I just wanted to avoid points where 3 lines intersect. But we need to count them as if they didn't intersect. Assuming that this is correct, what complexity do I have? For one red point, I will iterate over with whom I need to connect. Like for this guy, I said you're connected to this white, and then the next red is connected to next white. And for everything here, I can know the number of reds there, the number of whites here, and I think that the number of intersection with this line is minimum of reds here are up, let's say, comma, white down. Because as long as one of them is not over with this line, the first red connects with something and we have an intersection with my line. The next red is connected with something on the other side, then we are out of reds. So it's this number, plus additionally, if we move in the other way, so this red is connected to this white, and then the next red is connected to the next white, and then for the same reason I take reds down and whites up. So it's this plus the other way around. R down, comma, whites up. After preprocessing, that's quadratic solution to ask in some interval. Wait, there are n possibilities to connect this red thing. For each of them, I know what's the number of intersections with me in constant time, but I need to iterate over n other things and other lines. But maybe linear solution will be this. In this formula, up to some moment, because reds plus whites, there is the same number of reds and whites. So if I have my circle and I'm red there, and there are some whites I can connect to. It's not true that it's exactly the opposite white, but there is up to some moment here the number of, and that's not true. As I move forward with this connection, it's not true that the number of reds or that the number of whites will increase compared to the other one. Is it some kind of segment tree? Or if I move red by one, something will be modified in this segment tree? Because if I connect like that, and I have 4 whites here, and let's say 6 red, so here the red is times 6, then the minimum here is 4, and minimum in the other half will be reds. And assume that the number of remaining elements other than this pair, n minus 1. Okay, what's the number of pairs that don't intersect me? For those 6 reds. For all reds here, I have an intersection. For all whites here, there are too few reds there. First 4 of those reds will be connected well. But those reds will not. So the number of non-intersections is just the difference between the number of reds and the number of whites here. No. Here it's the number of non-intersections is reds down minus white up. It's this. And I think this is equal to whites down minus reds up. Because when I move stuff around, this to the left side, I will get from this red down plus red up is equal white up plus white down, and that's true because the total number of red and down is the same. Okay, so skip that. We have this, or I can say as well, if this is negative, then I just take the other sign. I think that's just the difference, the absolute value. I can also say that it's red down minus and minus 1 minus whites down. That works as well. So that n minus 1 minus reds down plus whites down, so just down. This is the number of non-intersections. It's a bit hard to believe. Is it? Okay, and this means just we try to split roughly in half. So down means just all points below. I care about the count of points here, both white and the I want to split points equally between those two parts. I minimize over the sum of this. And now up to some moment, if I consider different possible connections, up to some moment, this difference will be just, down will be bigger, so it will be down minus the constant. So I can binary search this point, kind of, for this red point, find the most opposite point, that's it. if we just consider all 2n-1 remaining points. Let's say it's this one, because there were a lot of red points here. Then, for everybody here, we say that the number of intersections, if we connect like that, is constant minus index, and here it will be constant plus index, or the other way around. It will be just a linear function. Let's treat it like that. If this is red point number 0 and white points are numbered 0, 1, 2, 3 and so on, then connecting this red point number 0 to some white point, I can say what that gives to the answer, and then when I consider any other, let's say the next red point, then connecting it with I plus 1 corresponds to connecting the point 0 with I. We are here now at 1. This was 0 among red points, this is 1 among red points. So I just need to add, again, for this guy, I need to binary search, or just use 2 pointers, to find the most opposite point. I don't even need to do that. We are given a string, so just for point I, it's point I plus half size of the string. And just say for all white points before that moment, we add constant plus index or minus, whatever, and for the other half, constant minus index. And that can be done with a, not even segment tree, I think it can be done with prefix sums at the end. Just for some interval to add function index plus minus 1 plus constant. This can be handled with prefix sums. I think that's it. But to make sure, instead of implementing this, which wouldn't be pleasant, I will wait for the editorial and I will talk with others about the problem. But I think I solved. I think I came up with solutions for the full score. If that changes, if I messed up something a lot, I will inform you about it in the comments, I think, of this video, in the pinned comment, so check there. And that's it for today. Thank you for watching. Links are in the description. Bye bye.